The Great Pyramid of Giza is a monument to human genius, not mystery. We have been asking the wrong question for centuries. Instead of wondering who helped them, we should ask how they did it themselves. This journey reconstructs the scientific reasoning embedded in ancient surveying practices. By the end, you will see history not as a collection of unsolved riddles, but as a clear record of methodical brilliance. We will uncover how celestial patterns became blueprints and how simple ropes encoded complex mathematics. This understanding reframes our entire past and reconnects us with a powerful, practical intellect. What part of the ancient world have you always assumed was built by magic long before blueprints or calculators? The very first surveyor was simply watching the world. Picture a Neolithic farmer, thousands of years ago, noticing a curious pattern. Each day, the stone marking the tip of a shadow cast by a staff would travel a certain path. Over the seasons, that path would shorten and lengthen with a perfect, predictable rhythm. This was not magic, it was the first scientific act, empirical observation. The entire discipline of ancient surveying rests on this foundation. It began not with complex mathematics, but with the relentless, repeated watching of natural phenomena. The sun, the stars, the steady flow of water in a canal, the unwavering line of a horizon, these were the original textbooks. The Roman engineer Vitruvius, centuries later, would codify this idea when he wrote that architectural design depends on symmetry, arising from proportion. But that crucial sense of proportion did not spring from a vacuum. It was painstakingly extracted from the observed patterns of the world itself. This process of watching and recording turned random notes into reliable data. Imagine the same community, generation after generation, tracking the sun's solstice points with those simple shadow markers. They weren't just marking days, they were building a database. From this mountain of observed consistency, something remarkable emerged, the standard unit of measure. Take the Egyptian royal cubit, a length of about 20.6 inches. Historians suggest this was not an arbitrary king's whim, but was likely derived from a geodetic or astronomical observation, perhaps a fraction of the Earth's circumference, or a relation to the swing of a pendulum. The unit became a physical token of observed cosmic order, a ruler literally grounded in the rhythms of the planet. This was the bedrock of all scientific reasoning to come. Observation led to measurement, measurement led to comparison, and comparison revealed the proportions Vitruvius spoke of. It transformed intuition into information. Think of your own life for a moment. The route you drive to work, the way your garden plants respond to sunlight, even your daily routines. These are patterns you've observed and now rely upon. You are, in your own way, building a personal science from empirical data. The ancients simply did this on a civilization-shaping scale, and their first tool was nothing more and nothing less than patient, attentive eyes fixed upon the heavens and the earth. That scribe drawing in the sand was decoding a universal language. Geometry was not an abstract school subject for the ancients. It was the sacred and practical syntax they used to translate cosmic order into terrestrial design. Historian of science Otto revealed how Babylonian mathematicians approached land division with an almost algebraic precision, solving for unknown lengths and areas. This was geometry in its most vital form, a toolset for imposing human intention upon the landscape. Consider the simple but profound 3-4-5 triangle. A surveyor stretching a rope divided into 12 equal segments could quickly create a perfect right angle by forming a triangle with sides of 3, 4, and 5. This empirical trick, understood and used for, is the practical heart of the Pythagorean theorem, proven much later. It was how you squared a temple's foundation or aligned a city's streets with the cardinal directions. The principle of similar triangles, where shapes share the same angles but different sizes, was another workhorse of ancient reasoning. By sighting along a rod and using simple proportions, a surveyor could measure the width of a river or the height of a cliff without ever crossing it. They were performing trigonometry with ropes and stakes. Even the constant we call pi, the ratio of a circle's circumference to its diameter, was embedded in their craft. The revolutionary invention of the wheel relied on an intuitive grasp of this relationship, and the circular foundations of many ancient structures show its practical application. The Great Pyramid's breathtakingly square base, with sides agreeing to within a fraction of an inch, is the ultimate monument to this applied geometric reasoning. It shouts that its builders spoke the language of shape and proportion fluently. This celestial mathematics then demanded physical instruments to be written upon the earth. These abstract principles needed hands to shape the world, and that is where the instrument became an extension of human reason. Think of the Roman, a beautifully simple device. It was essentially a cross mounted on a pole, with plumb bobs hanging from each of its four arms. By sighting along the aligned strings, a surveyor could project perfectly straight lines and exact right angles across miles of countryside. This humble tool was the engine behind the legendary straightness of Roman roads and the orderly grid of their military camps and new cities. It was not just a tool, it was a physical manifestation of a right angle, a portable piece of geometric certainty. The Egyptians had their own genius embodied in the Merkit. This instrument used a plumb line and a narrow sighting slot to track the transit of specific stars across the night sky. As archaeologist John has emphasized, the sophistication of such Egyptian tools reveals a culture that didn't just build by brute force, but by precise, repeatable celestial alignment. They were literally tying their temples to the motion of the cosmos. Later, the Greeks developed a more complex sighting instrument that could measure both horizontal and vertical angles, a direct precursor to the modern theodolite. Each of these inventions operationalized a profound abstract concept. A simple water level, a tube filled with water, gave physical form to the idea of a perfectly horizontal plane. A set of aligned sighting rods materialized the geometric principle of a straight line extending to the horizon. Their very designs reveal an intuitive grasp of stability, of immutable reference points, and of methods to minimize error. Look at your smartphone for a moment. Its global positioning system receiver is a tool that embodies the complex ideas of orbital mechanics and relativistic time correction to answer the ancient simple question, where am I? These ancient instruments, however, possessed a profound limitation that was also their greatest strength. They were utterly useless without a masterful understanding of the reference frames provided by nature itself. They could only create a right angle if the surveyor first established a true north-south line by watching the stars. The water level's horizontal plane was meaningless unless it was related to the actual slope of the land. This intimate dialogue between tool and cosmos is what separated true surveying from mere measurement. It forced the practitioner to be an astronomer, a geometer, and an engineer all at once, constantly cross-checking human artifice against the unwavering constants of the natural world. The solstice sunrise did not just illuminate the temple, it proved the temple's place in the cosmos. This fourth practice, celestial benchmarking, represents the pinnacle of ancient scientific reasoning. It is the act of using the sky itself as a perfect, unchanging grid. While they gave them right angles on the ground, the stars gave them an absolute reference frame in the heavens. The Egyptians achieved this with breathtaking precision. To align the Great Pyramid's sides to the cardinal directions within a fraction of a degree, they likely used a method involving the simultaneous observation of two circumpolar stars. As one star rose and another set, the midpoint between their positions on the horizon would point directly to true north. This was not a single person's job. It required teams of observers stationed miles apart, coordinated with simple timekeeping methods like water clocks, to take sightings on the same night. The result was an orientation so exact it rivals what we could achieve with modern tools. This principle echoes across the ancient world. At Stonehenge, researchers like Hawkins proposed that the monument's alignments functioned as a kind of astronomical computer, predicting solstices, eclipses, and other celestial events through the interplay of stones and the scientific reasoning here is profound. The local landscape is variable, hills rise and rivers shift, but the celestial motions are immutable, governed by laws beyond human influence. By locking a structure to a star's transit or the sun's extreme position, the builders integrated it into a cosmic order. It was a guarantee of perpetual alignment, a way to make stone participate in the rhythm of the universe. This fusion of high-precision astronomy with monumental engineering transforms these sites from mere buildings into philosophical statements carved in rock. They declare that human order is a reflection of celestial order, so look up tonight. Beyond the familiar constellations, find the steady pivot point around which the northern sky turns. That fixed point used for is more than a navigation aid. It is a symbol of the search for an unchanging truth in a changing world. Celestial alignment provided the grand framework, But measuring the Earth itself required another ingenious approach. The distance between two shadows in Egypt revealed the size of the entire world. This fifth practice, geodetic sourcing, is perhaps the most breathtaking leap of ancient scientific reasoning. It moves beyond measuring the land to measuring the planet itself, and then deriving your fundamental units from that grand scale. The story of Eratosthenes is the classic example. Around 240 years before the Common Era, this Greek scholar in Alexandria learned of a well in a city to the south. At noon on the summer solstice, sunlight shone directly to the bottom of that well, meaning the sun was perfectly overhead, casting no shadow. On that same day and time in Alexandria, he measured the angle of a shadow cast by a vertical staff. That angle was about 7.2 degrees, or roughly 1/50th of a full circle. He then needed the north-south distance between the two cities. This was likely obtained from professional pacers, men trained to walk in consistent, measured strides over long journeys. Using that distance and the simple geometric principle that the arc of the Earth corresponds to the angle of the shadow, he calculated the planet's circumference. His result was astonishingly close to the modern value. This was not magic, it was pure, elegant geodetic reasoning. He used the Earth to measure itself. This profound idea suggests something even more foundational. Scholars like John have explored the theory that ancient units of measure, such as the Egyptian royal cubit or the later sacred cubit, were not random. They may have been geodetically derived, representing a specific fraction of the Earth's polar radius or circumference. Another compelling theory links the cubit to a pendulum swing. A simple pendulum of a certain length, swinging with a 1-second beat at a specific latitude, produces a length remarkably close to the ancient cubit. Whether from the arc of the planet or the swing of a weight, the reasoning is revolutionary. By tethering their basic unit to a planetary constant, they created a measure that was inherently scalable and reproducible anywhere. It was a potential universal standard. Think of the chaos in a world of arbitrary measures. A king's foot here, a merchant's forearm there, all varying from town to town. Now imagine the transformative power of introducing a foot defined as 1/6 millionth of the Earth's polar radius. Suddenly, an architect in Memphis and a surveyor in Thebes could work from the same invisible blueprint, encoded in the very dimensions of the world. This fostered unprecedented coordination for trade, taxation, and of course, colossal construction. It meant the precise dimensions of a pyramid's base in Giza could be conceptually linked to a temple's foundation 800 kilometers up the Nile, because both were expressions of the same Earth-derived mathematics. How does standardizing measurements improve your own projects? Whether you're following a recipe, building a piece of furniture, or collaborating on a digital design, shared, reliable units eliminate guesswork and error. They allow separate efforts to combine into a coherent whole. For the ancients, this geodetic sourcing was the ultimate act of standardization. It provided the consistent, planet-scale ruler that made the next staggering feat possible, moving mountains of stone with the precision of a watchmaker. A multi-ton block of stone does not move by willpower alone. The sixth practice, megalithic logistics, reveals the ancient mastery of a practical calculus, the applied physics of mass and movement. Picture hundreds of workers not as a chaotic mob, but as a single, coordinated machine. Their task is to transport a granite block weighing as much as 70 tons from a quarry to a temple site miles away. They have no cranes, no diesel engines. What they possess is a profound, intuitive understanding of forces. Experimental archaeologists like Mark have shown us how this worked. The first principle was defeating friction. They would construct a wooden sledge and place the stone upon it. Then, ahead of the sledge, workers would pour water onto a prepared pathway of wooden rails or compacted earth, creating a slick surface of mud that acted as a lubricant. This simple act could reduce the required pulling force by over half. It was a brilliant application of an observed physical property. Next came the lever, a tool that embodies the principle of mechanical advantage. By placing a strong wooden beam under a stone's edge and using a smaller rock as a fulcrum, a team could apply force at the long end of the lever to lift the short end, incrementally raising the massive block. This was statics in action, a quiet calculation of weight, distance, and force playing out in real time. For the most daunting vertical lifts, such as placing the lintel stones atop the grate at Stonehenge, researchers proposed the use of earthen ramps and counterweight systems. Imagine a giant basket filled with stones on the opposite side of a pivot, its descending weight helping to hoist the megalith into position. This is dynamics, the management of moving weights and balances. The scientific reasoning here is a form of embodied mathematics. The builders did not write out equations for force vectors, but they understood them through the feel of a rope, the groan of wood under stress, and the visual alignment of a rising stone. Every action was part of a planned sequence. Transporting the stone was only half the battle. Its final placement demanded millimeter precision. At sites like in Peru, giant stones were fitted together with such tight joints that a razor blade cannot slip between them. This was achieved through a constant process of verification. Using water-filled trenches as long spirit levels and plumb lines for vertical checks, they would test, adjust, and test again, slowly lowering the stone into its perfect permanent home. The entire operation was a symphony of logistics, each movement calculated, each force anticipated. Think of the last time you moved a heavy piece of furniture. You likely nudged it, tested its weight, looked for the best grip, and maybe called for help. In that moment, you were performing your own small-scale version of this ancient calculus, breaking down a massive problem into a series of smaller, manageable physical actions. The master builders simply scaled this reasoning to a civilization-shaping level, turning intuition into a repeatable engineering protocol that could conquer mountains of stone. A still pool of water holds a secret more profound than any reflection. This seventh practice, hydrostatic leveling, gave ancient engineers mastery over the most elusive of geometric ideals, the perfect horizontal plane. For constructing something as vast as a Roman aqueduct, which had to descend at a precise, gentle slope over dozens of miles, or for laying the absolutely level foundation of a monumental temple, the human eye was hopelessly inadequate. A hill or a valley would utterly deceive it. The solution was not in the sky, but in the calm, obedient nature of water itself. The Greek engineer Hero of Alexandria, writing in the 1st century, described a simple device called a long wooden bench with water-filled grooves running along its top. When the water in both ends settled to exactly the same height, the bench itself was perfectly level. This was hydrostatic leveling in its most elegant form, a brilliant application of fluid mechanics understood through observation. The core scientific principle is beautifully simple. Water, at rest, always seeks its own level. This provided an automatic, objective, and reliable horizontal reference that was completely independent of the surveyor's potentially flawed perception. It was nature's own spirit level. To transfer this level datum across a valley or over the undulating path of a future aqueduct, ancient surveyors employed a method of stunning ingenuity. They would set up a series of interconnected basins, or use long, flexible tubes made from animal skins, all filled with water. By ensuring the water surface in the starting basin was at the desired height, they could then travel to the next point, and the water in that distant basin would settle at precisely the same elevation, regardless of the hills or dips in between. They were, in effect, creating a continuous plane of water, a liquid datum that faithfully traced a level line across any terrain. This practice reveals a deep, intuitive grasp of hydrostatic pressure and the engineering concept of a datum plane, a fixed reference elevation from which all other heights are measured. It is a cornerstone of all modern civil engineering, from laying railway tracks to planning cities. The quiet genius of this method lies in its surrender to a natural law. The builders did not fight the landscape, they used a universal fluid to reveal its true form. How do you find a level reference point in your own chaotic situation? You look for the constant, the unchanging principle that cuts through the noise. For them, it was the unwavering surface of still water. Once this universal horizontal was established across the land, a new geometric challenge arose, demanding equal precision in the vertical dimension. The stretched chord holds a truth more rigid than stone. This eighth practice, the ritual of the chord, represents the moment abstract geometry became an action you could perform with your own hands. Across ancient cultures, from the Vedic scholars of India to the planners of Mesopotamian cities, the primary tool for imposing order was not a metal instrument, but a simple length of rope. The sutras, ancient Indian texts of ritual geometry, detail with meticulous care how to construct perfect altars and ceremonial spaces using nothing but stakes and cords. The procedure was almost a dance. Drive a central peg, stretch a chord to mark a circle, then use intersecting arcs from other pegs to bisect lines and create perfect squares and east-west alignments. This was not merely construction, it was a ceremony that enacted mathematical law upon the earth. Similarly, Babylonian surveyors used knotted ropes, their segments forming known Pythagorean triples like 3, 4, 5, to generate flawless right angles for land division and temple foundations. The scientific reasoning here is beautifully operational. A right angle is an abstract concept, but a triangle with sides of 3, 4, and 5 units is a physical object you can create. By making the chord taut, they eliminated sag and error, transforming a geometric truth into a terrestrial fact. This ritual of stretching and pegging established the system of perpendicular lines that is the invisible skeleton of every planned city. The astonishing grid of Mohenjo-Daro in the Indus Valley, with its streets intersecting at perfect right angles, and the uniform, reproducible layout of every Roman military camp, or castrum, were born from this same simple act. The chord was more than a tool, it was a symbol of cosmic order and human intention, a literal line drawn against chaos. Where in your own projects do you need to establish a clear, correct standard, your own right angle, against which everything else can be measured? This precise, two-dimensional grid on the ground was only the beginning. The true test of their reasoning was to lift that perfect geometry from the dust and build it into the sky. A small clay model must hold the entire soul of a future mountain. The ninth practice, projective geometry, is the master key for unlocking a miniature vision and building it at a colossal scale. It is the art and science of scaling designs from a handheld plan to a living monument, and its most elegant tool was a simple square grid. In ancient Egypt, artists and masons did not work from complex blueprints as we know them. Instead, they first sketched their intricate scenes of gods, pharaohs, and rituals onto a plaster wall that had been carefully ruled with a red grid of squares. Each square represented a fixed module, often one royal cubit. The artist would draw the scene within this network of lines. Then, the masons would superimpose a larger, physically identical grid on the bare stone of the temple wall. By faithfully copying the contents of each small square into its corresponding large square, the design could be enlarged with perfect proportionality. A curve in a small grid became the same curve, just in the large grid. This is the core of projective geometry. It preserves all angular relationships and ratios, no matter how much you scale the image up or down. The scientific reasoning is one of controlled transformation. By fixing the design to an invariant grid, you remove the vagaries of freehand drawing over vast distances. It turns artistic intuition into a reproducible technical process. This modular system meant a master designer in Thebes could create a standard column capital or a decorative frieze pattern on a small grid. That design, recorded on a papyrus scroll, could then be sent to a worksite where a team that had never met the master could execute it flawlessly, simply by following the grid. It was an early form of digital file sharing, with the grid squares acting as pixels. This reasoning reaches its most refined expression in structures like the Parthenon. Its famous subtle curves, the gentle upward bow of the stylobate floor and the slight inward lean of the columns, were not accidents of settling stone. They were intentional refinements designed to correct optical illusions and enhance the feeling of vitality. To build these curves, the Greek architects went beyond a simple square grid. They used a system of off-grid projections, likely involving carefully calculated offsets from theoretical straight lines. Each stone in the curving sequence was uniquely shaped, its dimensions derived from its specific position in the larger flowing form. This required a profound grasp of how to project a complex three-dimensional idea from a plan onto the actual, irregular pieces of marble. How do you scale a small idea into a large, successful project in your own life? You break it down into manageable, repeatable modules, consistent actions, weekly goals, standardized processes that maintain the core proportions of your vision even as the work expands. For the ancients, this modular grid was the protocol that allowed hundreds of workers across decades to act as a single, coherent mind. But such a monumental undertaking generated an ocean of data, measurements, quotas, alignments, that had to be managed with the same precision as the stones themselves. A wet clay tablet waits to receive the memory of a civilization. This 10th practice, archival memory, is where the ephemeral craft of the surveyor was etched into the permanence of written record, transforming personal skill into a legacy that could outlast empires. Picture a Sumerian scribe in a dim administrative chamber, his stylus pressing precise, wedge-shaped marks into a soft tablet. He is not writing poetry or law, but something equally vital, a land survey record. This tablet documents field boundaries, irrigation canal lengths, and crop yields for taxation. In that moment, he is performing a profound act of scientific reasoning. He is codifying the spatial and quantitative reality of the kingdom into a standardized, retrievable format. This was the birth of data management. The reasoning is clear. Knowledge trapped in a single mind is fragile, lost when that individual passes. But knowledge inscribed on clay, papyrus, or stone becomes cumulative. It can be checked, taught, and refined across generations. The famed mathematical papyrus from ancient Egypt is essentially a textbook, a compilation of practical problems and solutions used for training scribes in geometry, algebra, and calculation, the very skills needed for surveying land and administering resources. It contains problems about calculating the slope of a pyramid or the area of a field. This was not theoretical math for its own sake. It was the procedure manual for running a state. By systematizing methods into repeatable rules and formulas, experiential craft evolved into a formalized discipline. Temples and royal scribal schools became the hard drives of the ancient world, repositories of this guarded technical knowledge. The continuity of architectural style across centuries of Egyptian history, or the consistent application of the Roman foot across vast territories, speaks to the power of this archived standard. It meant a young apprentice in Memphis could learn the same geometric proofs and rope tricks used by master builders 500 years prior. This system of archival memory enabled true technological progress. Innovations were not lost, but could be built upon. How do you ensure your own hard-won knowledge, whether from a personal project or a professional breakthrough, is preserved for those who come after you? You likely write it down, create a guide, or develop a repeatable process. That instinct to codify is the same one that drove the scribe to press his stylus into the clay. It is the bridge between individual genius and enduring civilization. This meticulously preserved library of techniques faced its ultimate validation not in the classroom, but under the blazing sun, where theory met the uncompromising reality of stone and scale. The Giza Plateau is not a collection of 3 separate tombs, but a single, integrated machine carved in stone. Its construction was the ultimate synthesis of every ancient surveying practice, a coordinated geodesy executed over generations. Stand on the desert floor and look east. The 3 Great Pyramids are aligned to the cardinal directions, with an accuracy that still stuns modern surveyors. The Great Pyramid sides deviate from true north by less than 1/10 of a degree. How was this possible? Engineer and archaeologist Glenn Dash has demonstrated a remarkably elegant method the Egyptians likely used. On a clear autumn evening, teams of surveyors would have marked the rising and setting points of a single circumpolar star, as it pivoted around the celestial pole. By bisecting the angle between these 2 horizon points, they could establish a near-perfect north-south line. This celestial benchmarking provided the absolute reference frame for the entire site. But orientation was only the first step. Before a single block was laid, the builders had to create a perfectly level foundation bed over 5 hectares of naturally sloping limestone bedrock. They almost certainly employed hydrostatic leveling, using a network of water-filled trenches to establish a uniform horizontal plane across the entire construction site, shaving down high points until the water's surface was even everywhere. This gave them their unshakable datum. Every measurement across this vast project relied on the consistent application of the royal cubit, a unit likely derived from geodetic or pendulum principles. This standard ruler meant that separate work gangs quarrying stone miles apart and masons dressing blocks on site were all contributing to a single, coherent geometric whole. The logistics of moving and placing over 2 million blocks with such precision speaks to a data-driven process of staggering organization. Experimental work suggests they used lubricated sledges on prepared causeways, employing levers and counterweights for final positioning. But the true genius is seen in the quality control. The near-perfect squareness of the base, with its sides agreeing to within inches, implies constant verification. Surveyors would have used stretched cords to check diagonals, ensuring that if both were equal, the corners were true right angles. This was not guesswork, it was a continuous feedback loop of measurement and adjustment. What can a modern project manager learn from this 4,500-year-old megaproject? The answer lies in the power of a unified plan, a shared standard, and relentless verification against an unchanging reference. From the desert sands, we journey to the damp highlands of the Andes, where a different civilization faced an even more formidable geometric challenge. The stone walls were threads in a living map. The Incas did not merely survey their capital, they wove it into a cosmic diagram using a system of radiating lines called. From the central temple of the navel of their world, 41 precise sight lines stretched out like spokes into the surrounding landscape. Each line was not an abstract surveyor's mark, but a sacred pathway connecting hundreds of shrines, or a spring, a distinctive rock, a hilltop, even a building. This was not just geography, it was a geospatial information system that organized their entire reality. Anthropologist Tom dedicated his work to decoding this system, revealing its staggering complexity. It functioned as a calendar, with different along the lines marking specific days for rituals and agricultural cycles by aligning with the rise and set points of the sun and moon. It was a framework for social organization, with different noble lineages responsible for maintaining specific and their shrines. Perhaps most ingeniously, it was a hydrological map, as many of the lines followed the paths of water channels, linking the management of this precious resource directly to ritual observance. Reconstructing the reasoning behind this system reveals a holistic genius. To establish these lines, surveyors had to possess an intimate, three-dimensional knowledge of the topography. They had to stand at and sight over miles of rugged terrain, selecting natural features or placing markers that would remain along the straight path. This required an understanding of astronomy to align markers with celestial events, and of hydrology to integrate the flow of water. The system demonstrates that surveying at its highest level could be the very framework for a worldview, a way of making the landscape itself speak the language of time, ritual, and community. How do you connect the different, seemingly separate areas of your own life, work, family, personal goals, into a coherent functioning system? The Incas used sight lines of stone and spirit. Other ancient minds, however, found profound meaning not in lines, but in the very shape of their most fundamental tools. A number can be far more than a simple quantity. In the ancient world, measurement often carried a hidden dimension, a layer of meaning where mathematics met metaphysics. This 13th analysis asks us to contemplate the idea that the dimensions of the Temple of Solomon, as described in sacred texts, were believed to hold cosmic significance. This was not unique to one culture. It represents a profound intersection where scientific reasoning and symbolic meaning became one and the same in the practice of ancient metrology. The reasoning here operates on two levels. On the practical level, a builder needs a reliable, consistent unit like the Cubit to execute a complex design. But on a philosophical level, that same unit might be chosen because its proportions, and the proportions it generates, were thought to echo the harmonic ratios believed to structure the universe itself. This concept is often called the music of the spheres, the idea that celestial bodies move in mathematical relationships that produce a kind of inaudible cosmic harmony. The Greek philosopher Plato wrote extensively about these ideal forms, the perfect geometric shapes and numerical relationships that he believed underlay all of reality. For a culture that subscribed to this worldview, building a temple was not just an act of construction, it was an act of participation. By designing its chambers, courtyards, and altars using these sacred proportions, they were literally grounding cosmic harmony in stone, creating a microcosm of a perfectly ordered universe. This dual purpose created a powerful feedback loop that actually strengthened the technical practice of surveying. The demand for symbolic perfection drove an extreme need for precision. You could not be sloppy with a measurement if that measurement was also a divine cipher. The slightest error was not just a practical flaw, it was a spiritual rupture, a failure to correctly mirror the cosmos. This immense pressure for accuracy pushed the development of better tools, more rigorous methods, and more meticulous verification. Conversely, when the builders succeeded, when the temple stood with breathtaking geometric harmony, that technical triumph was seen as validation of the entire symbolic worldview. The perfect building proved the truth of the perfect cosmic order. The reasoning thus became both empirical and philosophical. The surveyor checked his chord against the stars, and also against a metaphysical ideal. Think about a task in your own life that feels deeply meaningful, perhaps a family tradition you uphold or a personal project tied to a core value. You likely approach it with greater care, attention, and perseverance than you would a mundane chore. The meaning fuels the meticulousness. In ancient metrology, this symbolic layer often served as a vessel for encoding advanced mathematical concepts that might otherwise have been abstract and difficult to transmit. The golden ratio, a special proportion found throughout nature and art, frequently appears in the plans of temples and monuments not as a written formula, but as a lived spatial experience. A walking through a sequence of rooms whose lengths followed this ratio would physically feel its harmonic progression, internalizing a complex mathematical truth through architecture. The practice of measurement, therefore, was never just about the earth. It was a bridge between the tangible world of stone and shadow and an invisible world of number and essence, where every act of laying a rule was also an act of writing a prayer in geometry. A knotted rope is a silent library of unsolved equations. This 14th analysis asks us to look deeper into the simple tools we have already met, to recognize the advanced mathematical concepts they silently encoded. Take that surveyor's rope, divided by knots into 12 equal segments. By forming it into a 3-4-5 triangle, he created a perfect right angle. But the reasoning embedded in that act goes far beyond a handy trick. Those specific numbers are a primitive integer solution to the equation a squared plus b squared equals c squared. The repetitive practice of land division, of constantly needing to find missing lengths and areas, would have generated countless such problems. Through trial, error, and observation over generations, ancient practitioners could have inductively discovered patterns, entire families of what we call Pythagorean triples, long before Pythagoras formalized the theorem. The evidence for this is not speculative. The Babylonian clay tablet known as 322, dating to around 1800 before the Common Era, is essentially a trigonometric table. It lists 15 pairs of numbers that form the sides of right triangles, demonstrating a sophisticated working knowledge of these relationships for practical computation over a millennium before Greek geometry. This tablet was a calculator's reference sheet. The scientific reasoning here is profound. It suggests that advanced mathematics often grew from the soil of repetitive necessity, not from abstract contemplation. The rope, the shadow, the pile of counting stones, these were the abacus of the physical world. They were analog computers that allowed the mind to explore numerical relationships through tangible manipulation. By constantly using a 3-4-5 rope to square corners, a culture might gradually realize that a 5-12-13 rope also works, and then an 8-15-17 rope, slowly building a catalog of usable ratios. This challenges the clean, linear narrative of mathematical history. It proposes that practical empirical geometry, the knowledge of what works, preceded and informed the later formal proofs of why it works. The theorem was the final, elegant explanation for a truth that builders had been relying upon for centuries. Consider the square root of 2, an irrational number that cannot be expressed as a simple fraction. How could an ancient surveyor approximate it? If you take a square with sides of 1 unit, the diagonal is the square root of 2. By physically measuring and refining that diagonal with their ropes, they could arrive at a remarkably accurate fractional approximation, like 99/70ths, which is within 1/10,000th of the true value. This number wasn't just a curiosity, it was essential for scaling up designs from a square grid or for rotating structures by 45 degrees. The complex code running your favorite weather app or navigation software is hidden behind a simple, friendly icon. In the same way, the ancient world's most sophisticated mathematical reasoning was hidden within the worn fibers of a rope, the scratch marks on a tally stick, and the memorized chants of a land division ritual. These were the quiet, accumulated insights of countless unnamed practitioners, a distributed intelligence forged by the relentless demands of reality. And this very intelligence, this ability to model shapes and calculate relationships, was about to face its ultimate test, where a single miscalculation meant not a crooked wall, but a journey with no return. The open ocean offered no landmarks, only a shifting geometry of waves and light. For the Polynesian voyagers who settled islands across millions of square miles of the Pacific, surveying was not a practice confined to land. It was a dynamic, living science of navigation. They sailed across trackless blue using a mental map constructed from celestial motion, wave patterns, and the flight of birds. This 15th practice, maritime surveying, represents the ultimate extension of ancient reasoning into a fluid and unforgiving medium. On land, a surveyor could drive a peg and return to it tomorrow. At sea, the reference points were in constant motion, demanding a profound internalization of natural law. They learned to read the star paths. Specific stars were known to rise and set over specific islands, acting as celestial compass points. But a star's position changes with both the time of night and the season. To calibrate this moving map, navigators used horizon markers, a notch in a mountain range, or even stone enclosures on shore to memorize the exact spot on the horizon where a key star would appear at a given time of year. This was celestial benchmarking adapted for a vessel in motion. Their reasoning likely extended to sensing latitude. By observing how high a particular star passed directly overhead, its zenith point, they could gauge their north-south position. If the star passed directly above, they were at the island's latitude. If it passed to the north or south, they knew to correct their course. This is applied spherical geometry, reasoning on the curved surface of the Earth with the naked eye. The ocean itself provided data. Experienced navigators could interpret the refraction and patterns of swells, waves that had traveled thousands of miles, discerning the presence of distant islands long before they were visible. This was hydrostatic leveling reinterpreted for a vast, rolling plain. Closer to shore, for the crucial task of port construction, ancient engineers like the Romans applied more direct surveying methods. They would conduct soundings with weighted lines to profile the seabed, mapping depth to locate the best foundation for piers and breakwaters. They used the principles of similar triangles, sighting from cliffs to align harbor walls and calculate distances across water. Every voyage was an exercise in dead reckoning, a continuous calculation of position based on estimated speed, direction, and time, a supreme test of reasoning under extreme uncertainty with only the most basic tools. How do you navigate an uncertain environment with limited information? You rely on the deepest patterns you know, the constants you can trust, and you make tiny, continuous corrections. The Polynesian navigator, holding his course by the feel of the swell and the arc of a star, was the embodiment of ancient scientific reasoning in its most daring form. While they mastered the fluid geometry of the sea, on the solid continent of Asia, a different kind of long-distance reasoning was being etched into the landscape to bind an empire together. The straight line is an act of imperial will against the chaos of the landscape. A Roman, his planted firmly in the earth, was not merely measuring distance. He was imposing a geometric ideal upon hills, forests, and rivers. This 16th practice, route surveying, was the engineering logic that physically bound the empire together, turning conquest into permanence through roads, canals, and aqueducts. The corpus, the surviving manual of these land surveyors, lays out the method with cool precision. It instructs on establishing the rigor, the unwavering straight line, and the limits, the boundaries of the road's domain. But the true scientific reasoning is revealed in the adaptation. The goal was not a purely geometric line, but a functional one. Conquering topography meant calculating gradients gentle enough for laden carts, aligning tunnels through mountains from both sides, and planning intricate drainage to prevent washouts. This was applied mathematics in service of endurance. The process began with preliminary reconnaissance, scouts seeking the most efficient path that balanced directness with buildable terrain. Then Thea and his team would set out the master baseline using there, creating a series of straight sight lines across the countryside. When an obstacle like a steep hill or a marsh intervened, the reasoning shifted from imposition to intelligent adaptation. They would pivot the route in a calculated detour or undertake the massive labor of cutting or filling, always with the long-term function in mind. Each decision was a cost-benefit analysis in stone and labor. The resulting network, like the famed via, was more than a road. It was a systematic geospatial plan that integrated military speed, economic flow, and administrative control. A message could travel from Rome to the coast with reliable speed, legions could be deployed to quell unrest, and goods could move from province to market. The road was a linear engine of empire. Its durability, with some stretches still visible today, speaks to the soundness of the reasoning behind every graded curve and drainage culvert. What long-term infrastructure are you building in your own life? It might be a skill, a relationship, or a project. Like the Roman surveyor, you are likely balancing the ideal straight path with the real obstacles you encounter, adjusting your course while never losing sight of the ultimate destination. These terrestrial networks of stone and purpose found a perfect mirror in the sky. In the celestial maps they ultimately inspired. A clay tablet etched with the boundaries of a single field contains the seed of an entire world. This 17th analysis, the cartographic impulse, follows the human drive to transform a collection of local plots into a unified worldview, a journey from dirt underfoot to the curvature of the planet itself. The earliest maps were intensely practical, like the Babylonian city plan of showing temples, canals, and walls, a direct projection of the surveyor's measured notes onto a permanent medium. These were tools for administration, for resolving disputes, for managing resources. But the reasoning embedded in this practice held a greater potential. Each accurate local survey provided a trusted data point, a fixed location whose relationship to other points was known. The monumental leap was not in measuring more land, but in asking how all these separate, truthful measurements could fit together into a coherent whole. Greek thinkers provided the intellectual framework for this synthesis. Eratosthenes, with his calculation of Earth's circumference, gave the model its scale. Hipparchus, perhaps the greatest astronomer of antiquity, provided its grid. Frustrated by the inconsistencies of existing maps, he adapted the Babylonian system of celestial coordinates to the Earth itself, proposing a network of lines of latitude and longitude. This was a stroke of abstract genius. Latitude could be determined by measuring the angle of the sun or the height of the pole star, a technique within reach of ancient observers. Longitude was far more difficult, requiring precise timekeeping across distances, a problem that would not be fully solved for centuries. Yet the very idea of the grid was revolutionary. It meant that any place on Earth, once its coordinates were determined, could be plotted in relation to any other place, even if no one had ever traveled directly between them. This required a profound shift in reasoning, from direct measurement to theoretical modeling. The mapmaker was no longer just a recorder of walked paths, but a thinker who could sit in a library in Alexandria and, using reports from travelers and sailors, position a coastline he had never seen within an imaginary mathematical net stretched over a sphere. Claudius Ptolemy's world map in the 2nd century was the majestic culmination of this reasoning. It was riddled with errors, of course, vast continents misplaced and oceans truncated, but its true significance was its method. It synthesized centuries of disparate geographical data, good and bad, within that spherical coordinate system. The map became a tool not just for navigation, but for philosophical understanding. It visualized humanity's domain, prompting questions about what lay beyond the edges, about the arrangement of lands and seas. This cartographic impulse reveals a fundamental pattern of scientific thought. We gather reliable local data, we devise a theoretical model to explain how that data connects, and we use the model to predict, to explore, and to refine our understanding. Your own mental map of your city, woven from commutes, errands, and favorite places, operates on the same principle. You synthesize countless individual journeys into a coherent internal model that allows you to plan a new route without having taken it before. The ancient mapmakers were doing this for all of known existence, and in doing so, they were beginning to model the nature of knowledge itself, how separate truths combine to form a greater, if still imperfect, picture of reality. Aristotle's philosophy begins with the senses, but the senses of whom? The great philosopher championed observation as the foundation of knowledge, yet the most meticulous observers of his age were not in the lecture halls of the Lyceum. They were on the dusty plains, hands calloused from ropes, eyes strained from sighting stars. This reveals a profound philosophical truth about the ancient world, and perhaps about all discovery. Scientific theory is often the child of practical craft, not its parent. The Greeks had distinct words for this. Techne was the knowledge of the craftsman, the shipwright, the surveyor, a practical embodied skill for making and doing. Episteme was theoretical understanding, the knowledge of causes and principles which Aristotle pursued. The history of surveying suggests these were not separate realms, but a continuous loop. The technique of the rope stretcher, successfully dividing fields and aligning temples generation after generation, built an unshakable empirical confidence. The rule worked. The 3-4-5 triangle always produced a square corner. The bisected star points always found true north. This mountain of successful practice created the firm ground from which the flower of episteme could grow. The geometric theorems formalized by thinkers like Euclid were not sudden inventions from pure thought. They were, in large part, the elegant codification of rules that masons and land measurers had been using for centuries. The reasoning was bottom-up. The world, through relentless manipulation, measurement, and correction, whispered its structural secrets to those who worked with it daily. This challenges our romantic notion of the lone genius, the philosopher in his chamber discovering truth through sheer intellect. Ancient science was far more collective and incremental. It was a distributed intelligence, where the surveyor's empirical note, the scribe's archival record, and the philosopher's synthesizing mind each played a part. The formal proof was the final act, the seal of certainty placed upon a truth already known to be true because it had built the world. Your own understanding likely follows a similar path. The deep theory you grasp in any field often clicks into place only after you have struggled with the hands-on practice, after you have felt the problem in your own efforts. That practical epistemology, where knowledge rises from the earth upward, faced its greatest test not from a new idea, but from a profound historical rupture. No blueprint for Stonehenge was ever carved in stone. The most profound casualty of time is not the monument itself, but the reasoning that built it. The meticulous how-to manuals, the oral traditions passed from master to apprentice, the wooden models and wax tablets used for planning, these are almost entirely lost to us. This transmission gap creates a vacuum in our understanding, and nature, as we know, abhors a vacuum. Into this void rush two opposing modern impulses. The first is an underestimation, a dismissal that such feats must have been simplistic or accidental. The second, more popular and problematic, is a fantastical overestimation, leaping to explanations involving lost civilizations or otherworldly intervention. Both are failures of historical imagination, born from the same source. We have the breathtaking product, but we have misplaced the instruction manual. Consider something as intricate as the mechanism, that ancient Greek analog computer. We have its corroded bronze gears, but we do not have the design notes, the trial prototypes, or the conversations between the artisan and the astronomer who commissioned it. We see the stunning complexity of the outcome, and lacking the documented process, our minds struggle to chart a plausible path from concept to creation. The true casualty here is the step-by-step reasoning. Ancient engineering was likely far more iterative than we assume. A master builder did not conceive a perfect pyramid in a single visionary flash. He would have overseen the construction of smaller test structures, refined his leveling techniques on local projects, and developed a library of solutions to problems like quarrying, transport, and lifting through decades of hands-on work. This knowledge was embodied, stored in muscle memory and craft intuition, and transmitted through demonstration, not dissertation. When that unbroken chain of apprenticeship was severed by social upheaval, by the loss of a specialized guild, or simply by the passage of centuries, the why behind the how evaporated. What remains are the silent stones, and we are left to reverse engineer the thinking. This is a perilous but necessary endeavor. Modern researchers, like experimental archaeologists, rebuild ancient furnaces or attempt to move megaliths using period-appropriate tools. Their work is invaluable, yet it carries a subtle risk: the temptation to impose our own, modern thought patterns onto the past. We think in and equations. They may have thought in stories, rituals, and geometric harmonies. The process for aligning a temple might have been inseparable from a ceremonial chant that paced the measurements. The act of stretching the sacred cord could have been both a geometric operation and a spiritual invocation. Their scientific reasoning was likely elegantly different, more holistic, where calculation and meaning were not separate categories. This transmission gap is precisely where pseudoscience finds fertile ground. When logic seems insufficient to bridge the chasm between a problem and its ancient solution, the appeal of a shortcut, a mysterious lost technology, an outside intelligence becomes powerful. It offers a simple answer to a complex historical question. But the real task, the more rewarding one, is to resist that allure. When you encounter a gap in your own knowledge, a problem with no clear solution, do you assume an impenetrable mystery, or do you begin seeking the logical, if currently hidden, steps that must connect cause and effect? Bridging this gap is the quiet, rigorous mission of experimental archaeology and careful historiography. It requires humility to admit what we do not know, and creativity to reconstruct the lost middle steps of a brilliant human mind at work. The silent stones finally speak through the strain of modern muscle and rope. Experimental archaeology is the living laboratory where our theories about the past are put on trial by the unforgiving physics of the present. It is not reenactment, it is rigorous reconstruction, applying the full scientific method to ancient problems. A hypothesis is formed, perhaps about how a Stonehenge bluestone was moved from Wales. An experiment is designed using only materials and techniques available at the time. The team observes, measures, and records every detail: the exact angle of a wooden lever, the point where a hemp rope begins to fray, the number of people needed to pivot a 3-ton slab on greased timbers. The conclusion either validates the method or, just as importantly, reveals why it would have failed, sending researchers back to the drawing board. This process transforms romantic speculation into hard, quantifiable data. We learn not just that something could be done, but how, and at what cost in labor, time, and collective ingenuity. The celebrated NOVA documentary project that constructed a small-scale pyramid in the 1990s provided in this. Their team, led by archaeologists like Mark and stonemason Roger, tested everything from quarrying with stone tools to moving blocks on sledges. They discovered that wetting the sand in front of a sledge reduced pulling force dramatically, a simple yet profound bit of practical physics that ancient builders would have learned through trial and error. These experiments reveal the implicit knowledge that never gets written down. It is the precise spot to place a lever for maximum effect, the exact chant or rhythm used to coordinate a pull team, the intuitive feel for when a stone is about to tip. This is the techne, the craft knowledge that formal texts ignore. By physically struggling with the same problems, modern experimenters begin to think like ancient engineers, encountering the same bottlenecks and experiencing the same flashes of insight. They quantify the engineering tolerances, how level a ramp must be, how much a rope can stretch, how many calories a workforce would need. This turns vague notions of a lot of people into specific, manageable crew sizes and shift schedules. It is a direct, physical dialogue across. When you learn a new skill, like cooking or woodworking, you do not just read the recipe or the manual. You try it, you burn the sauce or cut the joint wrong, and in that failure, you understand the principle more deeply than any description could convey. These experimental teams are doing that for entire civilizations. Today, this hands-on work is increasingly augmented by digital tools. Three-dimensional scans of tool marks can be analyzed to reconstruct the exact motion of a chisel. Software can simulate the stress on a stone lintel or model the acoustics of an ancient chamber. We are not just building physical replicas, we are beginning to model the ancient mind itself, testing the decision trees a master builder would have faced when the foundation bed was not quite level or the quarry yielded a flawed stone. This fusion of mud, math, and muscle is closing the transmission gap, one reasoned experiment at a time. The subtle curve of a chisel stroke, frozen in stone is now a data point. We stand at the confluence of ancient craft and modern computation, where digital acts as a microscope for history. Technologies like LiDAR, which uses laser pulses to map terrain through dense forest canopy, and photogrammetry, which builds precise three-dimensional models from thousands of photographs, are revealing a hidden world. They allow us to scan the Great Pyramids casing stones and mathematically analyze the exact angles of their cuts, or to map the entire plateau from the air, tracing the sequence in which those vast were laid out. This is not just better photography, it is a fundamental shift in perception. We are now able to detect the fingerprints of ancient reasoning at a scale and resolution previously unimaginable. Ground-penetrating radar sends pulses into the earth, revealing the buried foundations of Roman villas or the subtle drainage channels beneath a Maya plaza, showing us the infrastructure hidden beneath the spectacle. When researchers digitally scan the intricate network of Roman aqueducts, They could calculate their gradients with millimeter precision, confirming the astonishing consistency of their gentle slopes over hundreds of miles. This data transforms a marvel into a mathematical equation. On a global scale, archaeologists are using big data analysis to compile the orientations of thousands of ancient monuments. By plotting temples, tombs, and stone circles on a map and analyzing their alignment patterns, they can search for statistical correlations. These digital surveys have suggested, for instance, that certain astronomical events, like the winter solstice sunrise, were targeted with remarkable frequency across disparate cultures. It hints at a shared, hard-won knowledge of the sky, a convergent scientific discovery written in stone and now decoded by silicon. The monument becomes a vast dataset, every weathering pattern, every tool mark, every slight deviation from perfect geometry, a whisper from the builders. This digital lens grants us a vision its creators might have, the ability to see their work as a complete measurable system. How might a new perspective, a fresh set of tools, reveal hidden patterns in a project you have been studying for years? This technological synthesis is quietly rewriting chapters of our history books, not with speculation, but with terabytes of immutable evidence. The label pre-scientific is a quiet dismissal echoing through history books. It draws a line, suggesting that before the philosophical academies of Greece, human thought was merely a collection of observations, lacking the rigorous method we call science. But reconstructing the precise, planet-spanning work of ancient surveyors dismantles that timeline entirely. We are not looking at pre-science. We are looking at a different, deeply sophisticated expression of it, one that was fully operational for thousands of years. The core components of the scientific method were present, not as abstract principles, but as the daily protocol of the craft. Methodical observation was the foundation, as seen in the generations of star trackers and shadow watchers who built celestial almanacs. Hypothesis testing occurred constantly through trial and error on the construction site. If we build the ramp at this angle, will the block slide or stick? If we align to this star, will the solstice light strike the inner chamber? Each project was a massive experiment, with success or catastrophic failure as the result. Mathematical modeling was embedded in the scaling grids, the geodetically derived units, and the projective geometry that turned a palm-sized sketch into a mountain of stone. This was not philosophy in the library. It was engineering in the field, a robust, iterative, and relentlessly practical form of reasoning that built the world. This revision is not a minor footnote. It fundamentally shifts the origin point of the scientific mindset and credits a far wider array of global cultures with foundational innovation. The intellectual leap of Eratosthenes measuring the Earth did not emerge from a vacuum. It stood on the shoulders of Egyptian surveyors who had been practicing celestial alignment and geodetic thinking for. The elegant proofs of Euclid formalized geometric relationships that Babylonian land division experts and Indian altar builders had been using as working rules for centuries. The story of technology is no longer a linear march from Greece to Rome to the Renaissance. It becomes a global tapestry, with parallel threads of discovery in the Andes, the Indus Valley, the Pacific, and the Nile Delta, each culture developing profound solutions to the universal problems of measurement, alignment, and control. This is a more inclusive and accurate history of human intellect, one that recognizes genius in the applied, in the maker's hands as much as in the philosopher's words. Does this recalibrated past change how you view the roots of your own field of study, whether it's engineering, design, or even project management? The legacy suggests that breakthrough often begins not with grand theory, but with a stubborn, practical problem solved through careful observation, iterative testing, and the courage to model a solution at scale. The future of innovation may well depend on remembering this broader, more grounded lineage. It teaches us to look for rigorous thinking in the workshop and the field, not just the laboratory, and to see in every ancient stone not a mystery, but a meticulously recorded data point in humanity's long experiment with reality. The stones do not simply sit together, they dance. During an earthquake, the precisely cut, interlocking blocks of Inca masonry shift and settle, then return to their original positions, a phenomenon modern engineers call dynamic rocking. This is not primitive construction. It is a brilliant, pre-industrial form of seismic base isolation. Today, we build skyscrapers on massive rubber and steel bearings that allow the foundation to move independently of the shaking ground, a high-tech echo of that ancient principle of flexible, intelligent connection. The parallel is profound. Both systems accept that immense force cannot be stopped, only redirected and dissipated. The Inca builder, working without mortar, created a structure that could flex and breathe with the living earth. The modern engineer, with advanced materials, achieves the same goal through calculated physics. This is biomimicry at the level of reasoning, not just form. We are not copying the look of a stone joint, we are rediscovering the deep logic of resilience that it embodies. This pattern of ancient insight inspiring contemporary solutions appears everywhere we look. The vast water catchment and conduit system of Petra, carved into rose-red cliffs, or the intricate based hydrology of the Maya were masterpieces of sustainable engineering. They harvested every drop of rainfall, channeled it through gravity-fed networks and stored it in reservoirs, creating oases in arid landscapes. These were not grand, energy-intensive projects, but elegant adaptations to local constraints, refined over generations through observation and necessity. Modern hydrologists, facing the challenges of climate change and water scarcity, are now looking back at these systems. They see in them a blueprint for decentralized, low-impact water management that works with the natural topography and climate cycles, rather than trying to overpower them with concrete and pumps. The reasoning embedded in these ancient practices is a quiet manifesto for our time. It demonstrates that the most enduring solutions are often born from deep adaptation, from a long conversation with a specific place and its limitations. The ancient surveyor was not a conqueror of nature, but a meticulous student of it. His alignments followed celestial constants, his foundations respected hydrostatic truths, and his structures were designed to endure within the local seismic or hydrological reality. This represents a paradigm of sustainable, resilient engineering that consumes little energy beyond human ingenuity and leverages natural forces instead of fighting them. In an era defined by resource scarcity and environmental fragility, this ancient toolkit of thought is being urgently reevaluated. What timeless principle from history could you adapt? It might be the modular grid for scaling a complex project, the use of a natural, unchanging reference point to maintain alignment, or the acceptance that some forces are best managed through flexibility, not rigid resistance. To apply these lessons, we must learn to see as they saw, not with nostalgia but with a renewed clarity. We must look at a problem and first ask, what does the environment itself suggest? What are the free constants, the inherent patterns, the unavoidable constraints? The answer, often whispered by the stones and the stars and the flow of water, has been waiting for centuries. The final lesson is not found in any ruin, but in a way of seeing. To truly understand the builders, we must attempt to think as they did. This is not about recreating their tools, but cultivating their cognitive toolkit. The core of their reasoning was built on 4 pillars. First, intense observation. This is more than just looking. It is a dedicated, patient study of patterns. Challenge yourself to spend a single day consciously tracking the sun's path across your window or noting how shadows lengthen and shrink. The goal is to move from passive seeing to active data collection, just as they did. Second, spatial visualization. This is the ability to hold a complex shape or alignment in your mind's eye, to rotate it, and to project it onto the physical world. Try leveling a table using only a cup of water as your guide, translating the flat plane of the water's surface into an adjustment of each leg. You are performing the same mental operation as the engineer checking a foundation with a water trench. Third, iterative prototyping. Ancient builders learned through doing, through small tests that informed larger actions. In your own projects, embrace the quick, low-stakes experiment, the rough sketch, the mock-up, the trial run. Each failure is not an end, but a crucial data point that refines the next attempt. Finally, holistic systems thinking. The surveyor never saw a single stone in isolation. He saw its relationship to the foundation's relationship to the horizon, and the horizon's relationship to the stars. This mindset connects the immediate task to the larger purpose and environment. Cultivating this gaze requires patience and a deep respect for incremental progress. It values practical elegance, the simplest, most robust solution, and it finds profound lessons in what does not work. How would adopting this surveyor's gaze change your approach to a daily problem? You might begin by observing its true shape, visualizing a solution from multiple angles, testing a small part of it, and considering how it fits into the broader system of your life. This quiet, methodical mindset was never an end in itself. It was always in service of a grander vision, a blueprint drawn not on papyrus, but across the canvas of an entire civilization. The chisel was never just a tool, it was a prayer in stone. In the ancient world, the surveyor's quest for precision was not a purely technical pursuit. It was a sacred and civic duty woven into a single, unbreakable thread. The drive to align a temple with the solstice sun served astronomy, yes, but it also honored the gods and demonstrated the pharaoh's divine mandate. The need to measure fields with exacting care was essential for fair taxation and feeding the city, which in turn maintained social order, which was itself seen as a reflection of cosmic order. Science, society, and the sacred were an inseparable trinity, each reinforcing the others. This profound fusion was not a limitation, but a colossal source of strength. It provided the social will, the organized labor, and the immense resources required for projects that pushed the very boundaries of what was technically possible. A society would not dedicate generations to moving mountains of stone for a mere engineering exercise. It would do so for a cause that touched every aspect of existence, from the spiritual to the economic. The pyramids are the ultimate testament to this, monuments where the precision of a right angle was as meaningful as the pharaoh's journey to the stars. This unity of purpose channeled the full creative and administrative power of a civilization toward a single, awe-inspiring goal. Contrast this with our modern world, where disciplines are carefully separated. Science often resides in specialized labs, spirituality in personal or communal spaces, and state policy in distant bureaucracies. This separation has yielded incredible, focused progress, allowing for deep specialization. But we might ponder what is lost when empirical reasoning is completely divorced from a shared, cultural narrative of meaning. Does a project undertaken solely for technical challenge or commercial gain inspire the same depth of commitment as one woven into the very identity of a people? The ancient model suggests that when rigorous, observational science is embedded within a framework of cultural purpose, it can mobilize human potential on a staggering scale. The question for us today is not about returning to temple worship, but about intentionality. Is there value in consciously reintegrating a sense of deeper purpose, of human and ecological meaning, into our own technical and architectural pursuits? Could our bridges, energy grids, and cities be designed not just for efficiency, but as expressions of resilience, community, and harmony with natural systems? The ancient surveyor's work was always pointing towards something greater than the plot of land he measured. His line in the sand was the beginning of a path that led to the heavens, guided by stars, and built to last for eternity. That sense of transcendent purpose may be the most powerful tool they ever wielded. The precise angle of a pyramid's slope might be its most important inscription. This leads us to a radical proposition. What if the primary purpose of these immense, precisely engineered structures was not merely to inspire awe or house the remains of a leader, but to actively encode and transmit knowledge across the abyss of time? We can view the monument itself as the ultimate product of ancient scientific reasoning, a form of Stone Age data storage designed for longevity that no clay tablet or papyrus scroll could ever hope to achieve. The reasoning here is profoundly future-oriented. By etching their understanding of celestial cycles, geodetic proportions, and harmonic geometry into the very alignment and shape of a mountain of stone, the builders created a permanent testament. It was a benchmark, a fixed point of reference that would outlast dynasties, languages, and even the memory of their own names. The Great Pyramid, for instance, is not just a tomb. It is a repository of data. Its cardinal orientation records a method for finding true north. Its base perimeter in relation to its height encodes a sophisticated approximation of pi. The angles of its shafts target specific stars, capturing a snapshot of the night sky as it appeared 4,500 years ago. This was against the fragility of perishable records. Libraries burn, scrolls decay, oral traditions fade, but a spanning a desert plateau or a stone circle weighing tens of tons remains. It is a silent teacher, waiting for a future civilization to learn the observational keys required to read it. The lines, when viewed from the correct vantage point, reveal their intricate animal and geometric forms. The precise solstice alignment of a temple doorway reveals itself only when the sun reaches its extreme position. The monument does not speak in words, but in relationships, angles to horizons, shadows to light, stone to star. It communicates a culture's highest understanding of cosmic order to anyone, in any age, who learns to look with the same meticulous eyes. Your own legacy, the knowledge and values you wish to pass on, might not be carved in granite. Yet the principle remains. What are you building, creating, or systematizing that is designed to communicate clearly to those who come after you, even if you are not there to explain it? It could be a family tradition, a well-documented project, or a simple set of guiding principles. The ancient builders chose the most durable medium imaginable, turning their entire landscape into a library and their greatest constructions into its most eloquent volumes. This brings our exploration full circle, back to the sheer awe that began our journey, but now seen through a lens of profound intention. That sense of awe was simply the starting point. We began this journey with a feeling of wonder at ancient precision, and we end it with a profound respect for the scientific reasoning that made such precision possible. We have reconstructed a world where observation was a sacred act, where geometry was not a theory but a living language spoken with ropes and shadows, and where tools were elegant embodiments of logical principles. From the Egyptian surveyors' celestial alignments to the Incas' landscape-spanning geometry, we have traced a global tapestry of human intellect, each thread representing a culture patiently unraveling the rules of the physical world. This exploration rewrites a familiar history. It transforms a story of impenetrable mystery into a clear testament to methodical, brilliant problem-solving. The legacy of these ancient practitioners is not confined to the stones they left behind. It lives in the very mindset of inquiry they pioneered, a mindset of patient observation, iterative testing, and a deep dialogue with nature's constants. Let their example be a quiet inspiration. Observe the patterns in your own world with fresh eyes. Approach a complex challenge with practical step-by-step reasoning. Build your projects, whether they are made of ideas or materials, with a clarity of purpose that connects the immediate task to a larger vision. If this reconstruction of ancient thought has reshaped your view of the past, consider joining us for more journeys into the rational heart of history's greatest puzzles. Which of these ancient practices, the celestial benchmark, the geodetic unit, the ritual of the chord, most fundamentally changed how you see their achievements? Your perspective adds another layer to this ongoing story of human discovery.